In this lesson, we're going to take a journey through time, from the Big Bang, nearly 14 billion years ago, through a sequence of events leading to the emergence of life on Earth. You're looking at pictures of some of the simplest life forms on Earth. These are bacteria cells. Bacteria are the smallest living things on planet Earth. Now, cells are composed of yet smaller particles called molecules, and molecules are composed of even smaller units called atoms. So you might be familiar with one important kind of molecule found in cells, and that's DNA. Here on the left here is the structure of DNA. It carries the recipe for building a living thing. Now, on Earth, it was DNA that captured this recipe for constructing life on some other planet, perhaps some other molecule is the hereditary material. But the DNA molecule itself is composed of atoms, and we see the little colored units here, and here's the key up here. So molecules are composed of atoms chemically bonded to each other in various complicated ways. So if we want to understand the deep history of life, we must first figure out the origin of atoms, the building blocks of matter in the universe. And the story of atoms goes back to the origin of the universe itself. And we think the universe had an origin event because of observations like those made by the Hubble Space Telescope. We have learned that scientists pointed the Hubble Space Telescope at a small patch of sky that appeared to have nothing, and after a long exposure, they found thousands and thousands of galaxies in that tiny patch of dark sky. What's more, all of the galaxies appear to be moving away from us. And there was a pattern to that movement. Galaxies that were close to us were moving away, but galaxies farther away were moving away faster, and galaxies the farthest away were moving away the fastest. So that's a pattern that would be explained by the expansion of the universe itself. So space is expanding and carrying galaxies away from each other. Well, if that's happening today, we simply sort of logically think that in the past the universe must have been smaller, so we can sort of reverse time and imagine the universe must have had an origin event, and the data suggests somewhere around 13.8 billion years ago. So it was the origin of the universe itself that led to the origin of matter that we call atoms, and some of those atoms will assemble into life in our universe. So that idea is nicely captured by a quote from Carl Sagan: "To make an apple pie from scratch, you must first invent the universe. To make a living thing, you must first invent the universe." In the remainder of the lesson, we're going to use two diagrams here to chart our course through time. On the right here is our sequence of events leading to the emergence of life in the universe, and on the left here is a sort of a timeline of important events in the history of the universe. So the Big Bang will be here on the left, and then the universe today on the right. And we have a time scale down here as well. So the Big Bang set off a sequence of events in which new things and processes emerged over time, including life. So we're going to be looking at the origin of simple elements like hydrogen and helium, and the origin of the first stars and galaxies, and then heavier elements, and then planets, chemistry, and life. We could also say that this diagram here on the left represents the cosmos, all that is, all that was, and all that will ever be. So let's begin the story then with what scientists call the Big Bang. Now, scientists today would say there's lots of evidence for the Big Bang, so they have high confidence in the following: that the universe was smaller and hotter in the past, then space-time expanded rapidly and continues to expand today, as observed by Edwin Hubble back in the 1920s and the Hubble Space Telescope today. So here we're showing the universe 13.8 billion years ago at a volume that is much smaller than the size of an atom. And then there's a rapid expansion of space. The universe, in a sense, was expanding. And here we're showing some of the components or the constituents of the universe here. We'll get into that in a moment. So the idea then is that all matter and energy today have origins in this earliest universe. In addition, the laws of nature that govern how matter and energy interact, they too were baked into the structure of the universe. And by laws of nature, we mean the forces, for example, gravity, the electromagnetic force, the nuclear forces. These are the things that kind of influence how energy and matter interact, and space itself and time even would have its origin with the Big Bang. Now, it was important that as the universe expanded, the overall temperature of the universe began to cool down. And that was important because it set the stage for an important transition that we'll see in the next step of our sequence. Over here on the right, we have the Big Bang, and then energy transformed into particles of matter. On our diagram over here, we're at this stage. We have the Big Bang on the left, we have the rapid expansion of the universe, and the universe was cooling down, and that allowed for energy to be converted into matter. Now, you might be familiar with one of Einstein's famous equations, E equals mc squared. The E stands for energy, the M for mass, and the C for the speed of light. And what Einstein's saying here is that energy and matter are sort of two sides of the same coin. Energy can be converted into matter, and matter can be transformed back into energy. So the energy of the early universe, as the universe cooled, that energy got transformed into particles of matter. Here I'm showing three of them here, a proton, an electron, and a neutron. And you might already know that these are the building blocks of atoms. So a very important transition happened early in the universe. The energy in the universe was transformed into material particles, particles of matter, the building blocks of atoms. In fact, this single particle, a proton that has a positive charge, that is the nucleus of a hydrogen atom. And at this stage, no other elements yet existed, and we'll get to what an element is in a moment. So that brings us then to the next transition. Over here on the right, we'll see the formation of hydrogen and some helium. So we've got the Big Bang, the energy being transformed into particles of matter, these subatomic particles that will assemble into hydrogen and helium atoms. But before we get to the atoms, the story begins with the formation of the nuclei of those atoms. So the early universe was hot enough to fuse hydrogen nuclei into some helium nuclei. And on our picture up here, that's this area right here. Nuclear fusion begins. Okay, so now let's get to this issue of what do we mean the early universe was hot? Well, temperature is a measure of the average energy of motion of particles. If particles are moving slowly, if the average motion of the particles is slow, they have low energy, then we say the temperature of that volume is low. If the particles are moving very quickly, right, so the average motion of those particles is fast, so they have a lot of energy, then we say the temperature of that volume will be higher. So as the universe expanded, it was very, very hot in the beginning, but as it expanded and more space was created, it began to cool down a little bit. So still, though, in the early hot universe, a very important event happened. We can see that here. The idea is that when the universe was very hot, all of these particles that were made, the protons and the neutrons and the electrons, they were buzzing around at high speeds and high energies and colliding in violent collisions. If we were to peer into the universe at this stage, the universe was a hot and dense fog. Light, the little photons of light would be colliding with electrons and being absorbed and then re-radiated, and you couldn't really see anything. It would have been just a fog, a really hot, dense fog of energy and particles smashing into each other. Now let's follow this hydrogen nucleus, just a proton here, and some interesting things can happen when these particles are smashing into each other with high energies. So let's take two protons down here. Now if the energy is sufficient, one proton, when it collides into another proton, that energy of that collision can actually transform one of the protons into a neutron. And then they might stick together. And we see one of those particles up here. We have a proton stuck with a neutron. So there's lots of weird stuff that goes on, and we're not going to get into the particle physics of that. But you just have to kind of think about just all these particles smashing together, and when they smash together with high energies, sometimes particles can change their identity. A proton can turn into a neutron with other particles. A neutron can turn into a proton with other particles flying around. So it's a complicated bit of particle physics here, but that's what was going on in the early universe. Now, what's the significance of that? Well, down here in this part of the diagram, we're showing an important event that was occurring. Here we have a proton and a neutron, and a proton and two neutrons smashing together, and the result is this bit down here, which is the nucleus of a helium atom, and then one of the neutrons flies off here. So what we've got, in a sense, is hydrogen being smashed together to form a helium nucleus. And this is what we call nuclear fusion. So the universe was hot enough for nuclear fusion to occur, and this is the process that happens in stars today. The way we describe this is that hydrogen nuclei are fusing to form a helium nucleus. Now, how much of this went on? Well, about 8% of the nuclei at the end of this stage, 8% were helium nuclei, and 92% remained hydrogen. So at this stage of the universe, after this stage of nuclear fusion, still the universe was mostly hydrogen nuclei, and with 8% being helium nuclei. Now, at this early stage, it was still too hot for atoms to form. Atoms, as we'll see, are when electrons are surrounding the nucleus. Well, it was too hot. The collisions were too violent, too energetic for the formation of atoms. And also, if particles were to kind of clump together by gravity, still the collisions were so violent that they would be knocked apart as well. So the influence of gravity is not important here, and atoms have yet to form. But because the universe continued to expand, temperatures got cooler and cooler, and that set the stage for our next event, the full formation of atoms. And the simplest atoms we're talking about are hydrogen and helium. So again, on the left here, we have the hot universe, but as it expands, it cools, and it cools to such an extent that the electrons that were buzzing around could be captured by protons. Electrons are negatively charged, protons are positively charged. So since particles were moving more slowly, protons could capture electrons, forming the first atoms of hydrogen and helium. So this is one of the forces in nature, the electromagnetic force. It's that force of attraction between oppositely charged particles. So we can think of the electrons, because the universe was cooling, the electrons and protons had slower motions, and that allowed the force, the attractive force, to capture electrons, and we have the formation of a hydrogen atom. Down here we have a helium atom. So the nucleus of the helium atom could capture 2 electrons, and that's the structure of the helium atom. Now, hydrogen and helium are 2 of the 92 naturally occurring elements. So here you're probably familiar with the periodic table of the elements. At this stage in the universe, only hydrogen and helium existed. But let's well, maybe there were trace amounts of lithium, but we'll ignore that for now. So let's define what we mean by elements. Elements are substances composed of a single kind of atom. Atoms are tiny particles of matter made up of smaller particles, as we've seen, protons, neutrons, and electrons. And the protons and neutrons of an atom are found in the nucleus of the atom, while the electrons orbit the nucleus. An element's identity is determined by the atom's identity, which is given by the number of protons in the nucleus. So let's take a look at the structure of some atoms. Here we see hydrogen on the left, and again it's an electromagnetic force that sort of holds the electron near to the nucleus of the atom, the proton. In a helium nucleus, we have 2 protons. Now notice though, positively charged particles will tend to repel, but that's where the neutrons come in. The neutrons, in a sense, are keeping the protons together. So this is a nuclear force that is keeping the nucleus of the atom together. So the protons are held together by the neutrons. So notice that a hydrogen atom does not even have a neutron. It's just one proton. The helium atom has two protons, and therefore a requirement to have some neutrons to hold them together. We have two electrons that are surrounding the nucleus of the helium atom. So we can think then, in the early universe, what was happening during this early hot stage was that the simplest nucleus, a single proton, the nucleus of the hydrogen atom, was the ingredient to make the next simplest element, helium. So helium formed from the fusion of hydrogen in the early hot universe. And that's what we're going to see in this table, the periodic table of the elements, that the universe has a history, and these elements had to be constructed out of something. Well, helium was constructed out of hydrogen. And we're going to see all the rest of these elements were also built by other processes that we'll get to in a moment. There was a little bit of lithium made in the early universe. This picture would be a lithium atom. It has 3 protons and 3 neutrons. So the neutrons are necessary to hold the protons together in the nucleus of the atom, and then it has electrons that are surrounding the nucleus. So now we're ready for the next transition. We have the universe is a giant cloud of hydrogen and helium, and now gravity is going to become the star of the show, that those clouds of hydrogen and helium will be compressed by gravity to form the first stars. So it took time for gravity to compress clouds of hydrogen and helium and ignite the first stars. In fact, on our picture here, we're at this stage here. It's called the Dark Ages. So at this stage of the universe is just filled with lots and lots of hydrogen with some helium. So there were no stars yet. But gravity is going to act on those clumps of matter and produce the first stars. Now here we have a picture of our sun on the left. Using a solar filter and a small telescope, we can see some sunspots here. And of course we know that our sun is a star just seen close up. So this is what we're talking about, the origin of the first stars in the universe. Well, those first stars necessarily were composed out of the only materials in the universe, hydrogen and helium. So this is what stars are made of, hydrogen and helium. Mostly hydrogen, as we saw. Now, how does a star form? Well, up here on the left here, we have a cloud of hydrogen. Now, the H2 is referring to hydrogen molecules, so 2 atoms of hydrogen chemically bonded together. So this is hydrogen gas. So we have giant clouds of hydrogen gas. All material particles feel the force of gravity, which is an attractive force. So gravity will tend to clump these clouds of hydrogen gas and pull more hydrogen into this volume here, and gravity will then begin to compress those clouds inside the core of the cloud. The temperature will increase, the pressure will increase, and at a certain point it gets so hot that the molecules break apart into individual atoms of hydrogen, and then it gets so hot and under such pressure that the atoms themselves begin to break down. So the collisions between those atoms are so great that the electrons get ripped off of the nucleus of the hydrogen atoms, and we have what scientists call plasma. Well, that's the very kind of stuff that we saw in the early stages of the universe. It was so hot that atoms couldn't maintain their structure. The collisions were so violent that the electrons were knocked off of the nuclei of the atoms. That's the plasma, and that's what is found inside the core of stars. And when it gets hot enough and under sufficient pressures, what we have then is nuclear fusion occurring. So here again, it's this fusion process in the core of a star, the very same kind of fusion process that was happening in the early universe. So stars emerge in the universe. If you take some hydrogen, some gravity, and time, you can get a star. In fact, in this picture, we're showing 2 sort of forces at play. The energy released from nuclear fusion tends to expand the star. Gravity tends to compress the star. When those 2 forces are sort of balanced, you get a stable star. And the energy from the nuclear fusion is radiated out into space as light and heat and other high-energy particles. So here's our sun. It is a star. And what's happening in the core of that star is fusion. Hydrogen nuclei are being fused to form helium nuclei, and that process releases energy. And that energy heats up the surface of the star, and hot things glow. And so we see the light coming, and light and heat coming from our sun. Here's a reminder that there are two kind of forces at play. The fusion force tends to expand the star. The gravity force tends to compress it. And when those forces are balanced, we have a stable star. Okay, now let's introduce a new concept here. On the left here, I've got the periodic table of the elements. And on the right, I've drawn a simplified version of some of the atoms of those elements. And let's remind ourselves that an element's identity is determined by the atom's identity, which is the number of protons in the nucleus. So here's the new concept. A heavier element is one whose atoms have more protons in the nucleus compared to other elements. So let's begin with the hydrogen atom. It has one proton, and hydrogen is up here on the periodic table. Here's hydrogen. Well, helium has two protons. That's what makes it helium. So here's helium with two protons. Now, I'm not showing the neutrons in these diagrams because we're focusing on the number of protons, which determines the identity of the element, the identity of the atom of that element. Lithium has 3 protons. Lithium on the periodic table is up here. Beryllium has 4 protons. Boron has 5. Carbon has 6. Let's take a look at carbon. 6 protons in the nucleus of the atom. Up here, nitrogen has 7. Oxygen has 8. Let's take a look. Nitrogen has 7 protons. Oxygen has 8. So what we're seeing then is that atoms have unique identities determined by the number of protons in the nucleus of the atom. Now, it's a simple matter then to define a heavier element is simply an element that has more protons than an atom that has less protons. So oxygen is heavier than nitrogen. Nitrogen is heavier than lithium. Or we could say it the other way. Helium is lighter than oxygen. So that's all we mean by lighter and heavier elements. Now you'll notice then that what stars were doing when they fuse protons together, the hydrogen nuclei to make helium, they're simply just smashing the lighter element to make a heavier element. And this can occur when you have sufficient temperatures and pressures. So under high temperatures and pressures, right, particles have lots of energy, and when they collide, interesting things happen, and you can fuse hydrogen nuclei to form a helium nucleus. So the lighter element hydrogen, is being used to make a heavier element helium. That's what's going on in the cores of stars. That brings us then to the formation of the first stars. And with the formation of the first stars, of course, then we get the formation of the first galaxies, because galaxies are collections, large numbers of stars bound by gravity. So here we are, 200 to 300 million years after the Big Bang. We have our first stars in star clusters, and then gravity will merge some of those star clusters to produce larger galaxies. Now here's a beautiful star cluster, a picture taken by the Hubble Space Telescope. And a star cluster is just that, a cluster of stars. There might be hundreds of thousands of stars here. Now if we're imagining these stars today to be the first stars in the early universe, then we have to imagine these stars did not have rocky planets. So there were no planets yet in the early universe here. And why is that? Because the elements to make rocky planets were not yet created. And based on our understanding of life on Earth, there could be no life possible at this time either, for the same reason. The elements found in living things were not yet created in large quantities. So the first stars emerged around 200 to 300 million years after the Big Bang, and that's all there would have been in the universe then. These early stars composed of hydrogen and helium, no planets in orbit around any of these early stars. But gravity was operating on these star clusters to merge them together to form larger galaxies. And here we see a sort of a spiral galaxy. And the stars are in motion here because of the original motion of the clusters. As gravity pulled them together, they then arranged themselves into these kind of disk shapes, what we call a spiral galaxy. We, of course, live in a galaxy called the Milky Way galaxy, shown here. Well, that picture of a star cluster there. That actually was photographed in a structure called the Large Magellanic Cloud. It is a small galaxy outside of our own Milky Way galaxy. Let's take a look at our Milky Way, though. So if we kind of just make a drawing of the Milky Way, here we see the spiral galaxy. Our solar system, our sun, is approximately at this location. So we're out on one of the spiral arms of the galaxy, and our sun is orbiting the core of our galaxy. This galaxy is a very large structure, so it's about 100,000 light years across. So it would take light 100,000 years to go from one side of the galaxy to the other side of the galaxy. But if we were to take a picture in the night sky of our Milky Way, what you're doing is you're orienting your camera towards the core of the galaxy. And when you do that, you can get a picture like this. So here we see the core of the galaxy in the center here, but we see this dark material here. This stuff would be the material in one of the arms of the galaxy that's between us and the core. So we'll talk more about what all this stuff is coming up later in the lesson. Here's a picture of our Milky Way galaxy, but we also see the two Magellanic Clouds, the Large and the Small Magellanic Cloud, only visible in the southern hemisphere. So these are clusters of stars that are outside of our own disk, our own spiral galaxy, the Milky Way galaxy. Now, if we expand our scale here, here's the Milky Way, here are the Magellanic Clouds. We do have other galactic neighbors. Here's a big galaxy over here about 2.5 million light years away, and that's the Andromeda galaxy. And this is a picture of Andromeda with a small telescope. So it too would be consisting of hundreds of billions of stars bound together by gravity. Now, if this were an early galaxy, again, it would just be stars. There would be no planets, no life at this stage in the early universe. And of course, the Hubble Space Telescope reminds us that our universe is populated with hundreds of billions of galaxies. And if we think of an analogy here, so here we have a spiral galaxy here, and that's just one of the galaxies in our universe. If this cube represents the entire observable universe, then a galaxy would be one of these little dots here, right? There are hundreds of billions of galaxies in our universe. But let's think about an analogy. If we were to take the size of the observable universe and shrink it down to the size of a classroom, well, how big would a galaxy be? It would be a particle of dust. So our universe is vast. We live in one galaxy, the Milky Way galaxy, one galaxy out of hundreds of billions of galaxies in the observable universe. So in part 2 of our story, we'll look at the next transition. The earliest stars in the earliest galaxies are going to be doing something very, very important. They're going to be cooking, they're going to be forging, they're going to be creating the heavier elements out of which planets, rocky planets like Earth, are composed. And on one planet we know of, the Earth, some chemistry went on to produce life. So we'll pick up the story in the next part.